Hello everyone. So now I will continue the chapter 4 and today we'll complete it within two more parts which will include the room problem जिससे अभी latest exam में question आया है and of course the other leftover part from the JD Winter book itself. So contact relationships of plutons. So general interaction at contacts. Juxtaposition of hot viscous magma with cooler stationary country rock leads to a chemical and mechanical interaction. Contact zones may have diagnostic structures and textures but can obscure simple relationship. So what it wants to say कि क्या होता है कि जब आपका hot viscous magma जो है वो आपके किसी कूलर बॉडी के साथ कांटेक्ट में आता है तो ये एक केमिकल और मैकेनिकल इंटरेक्शन जो है उसको रोल प्ले करता है. कॉन्टैक्ट जोन्स जो हैं उनके डायग्नोस्टिक स्ट्रक्चर्स और टेक्सचर होते हैं बट कैन ऑब्सक्योर सिंपल रिलेशनशिप. टाइप्स ऑफ कॉन्टैक्ट. शार्प कॉन्टैक्ट. इग्नियस रॉक डायरेक्टली एब्यूटिंग रिलेटिवली अनऑल्टर्ड रॉक उसको शार्प कॉन्टैक्ट कहेंगे. ग्रेडेशनल बॉर्डर जोन एक इंजेक्टेड जोन ट्रांजिशन फ्रॉम कंट्री टू एग्मेटाइट जोन विद जेनोलिथ्स एंड वेन्स. We have a figure, you can refer to this figure. Permeation zone, fluids, saturated plutons alter or partially melt the country rocks resulting in gradational boundaries. So permeation zone is that combined injection and permeation. It's a hybrid rock that formed due to mixed processes. So what it wants to say कि जब contacts होते हैं तो sharp contact होते हैं और एक gradational border zone होता है जो कि तीन उसमें divided है. Injected जब कोई transition होता है country rocks से एग्मेटाइट जोन तक उसके अंदर जेनोलिथ्स और वेन्स होंगे. परमिशन जोन एक फ्लूइड सैचुरेटेड प्लूटॉन्स होता है जो कि आल्टर करता है या फिर ऑल्टर और पार्शली मेल्ट country rocks and results in the gradational boundaries. We have combined injection and permeation together. Now we have thermal effects. So thermal processes can create distinct recrystallization zones, particularly with hot and dry intrusions. Now silica saturated fluids from the plutons can come from a contact metamorphic role, impacting country rocks more than the plutons. Now, we have the structures within the plutons. We have xenoliths, so fragments of country rock within the pluton, that is xenolith. Chill zone, a fine grain margin due to rapid cooling against the country rock, that is known as chill zone. Okay. Now we have one thing you need to about it कि ये फाइन ग्रेन होता है मार्जिन. इसके अंदर रैपिड कूलिंग है इसलिए फाइन ग्रेन है कूलर अगेंस्ट कूलर कंट्री रॉक्स. नाउ वी हैव shear zone. We have distributed shear in viscous magma near the contact leads to the lineation and foliation. So now we have scalene. It's an elongated mineral aggregates or ductile xenolith. External shear may rotate foliation in country rock making discordant contacts appear as concordant. So you need to know about the term scalene and as well as कि external shear जो है वो आपके foliations को country rock में rotate कर देते हैं जिसकी वजह से वो discordant दिखते हैं. Discordant जो है वो concordant दिखते हैं. Now we have post emplacement shearing. So later deformation along Pluton margin, they may superimpose tectonic features, potentially obviating original igneous textures. Now we have the timings of intrusion. So Pluton timings and tectonics. So post-tectonic plutons, they have been emplaced after the deformation and metamorphism. They are discordant to regional fabrics, but it may overprint emplacement-related structure sometimes. Now we have syntectonic. So it is emplaced during orogeny. Regional foliation continuous with emplacement-related foliation. Now we have pre-tectonic plutons emplaced before orogeny. Internal foliation parallels regional fabric due to deformation. Now we have challenges in distinction. So syn and pre-tectonic plutons may share similar features which might get sometimes difficult to differentiate between them. Most pre-tectonic plutons relate to earlier orogenic events in the multiply deformed belts. So now we have depth of intrusion. So based on the Grubenman 1904, we have three types of depth zone. We have epizone, we have mesozone, we have catazone. You need to know what depths they are, having. Epizone less than 8 kilometers. So cool, brittle country rock that is less than 300 degrees Celsius. And the characteristic is they are sharp, discordant contacts with brecciated wall rocks. Small intrusive bodies like stalks, cupolas with isotropic textures. Myelolytic cavities are common in it. This is the point you need to remember. Hydrothermal alteration and ore mineralization along the fractures, so that is somewhat present in epizone. Now we have mesozone up to 5 to 15 kilometer. Country rocks are sometimes at low grade metamorphism. It has a temperature range of 300 to 500 degrees Celsius. It has less than 300 degrees Celsius. It's a transitional feature between epizone and catazone, and they are foliated regional and contact metamorphic fabrics. Now we have chill zone, minor or absent. Now we have catazone that is more than 10 kilometer. It's medium to high grade regional metamorphism and has a temperature of 450 to 600 degrees Celsius. Characteristics: same tectonic emplacement with concordant gradational contact that is present in catazone, like they've been formed when the origin is there, and high ductility of country rock can lead to shear and foliation continuity. Now we have partial melting of country rocks that may occur and they create a mixed igneous metamorphic zone. So dynamic zone boundaries. So depth zones are not static. Rock may move between the zone due to burial, uplift, or thrusting. Now we have multiple injection and zone plutons. Complex intrusive histories. So large batholiths consist of numerous individual intrusions over extended periods. Example: Sierra Nevada batholith. And even smaller bodies often exhibit multiple intrusive events. Now we have just a minute. So what's the key takes like we have to take from here? So हमें पता है कि जो आपकी कॉन्टैक्ट बॉडीज बनती हैं तो कैसे बनती है, शार्प कॉन्टैक्ट होता है, ग्रेडेशन होता है, उसमें फर्दर 3 टाइप है: इंजेक्टेड, परमिएशन जोन एंड इनका कंबाइंड इंजेक्शन है परमिएशन जोन. वी हैव थर्मल इफेक्ट, वी हैव द स्ट्रक्चर्स विद इन द प्लूटोज दैट इज एनोलिथ, चिल जोन, वी हैव स्किलन, वी हैव द टाइमिंग्स के हिसाब से इंट्रूजन, पोस्ट टेक्टोनिक, सिन टेक्टोनिक, प्री टेक्टोनिक. एंड सिन और प्री में आप समटाइम्स हम फ़र्क नहीं कर पाते. फिर डेप्थ ऑफ इंट्रूजन की वजह से वी हैव एपिजोन, मेसोजोन एंड केटाजोन. फिर जो कैटाजोन होते हैं वो सिंटेक्टोनिक एप्लेसमेंट विद कॉन्कॉर्डेंट ग्रेडेशन कॉन्टैक्ट आ जाते हैं. नाउ वी हैव द मैग्मा राइज एंड एम्प्लेसमेंट एंड हाइड्रोथर्मल सिस्टम. सो वी हैव फर्स्ट एंड सेकेंड ओवर हेयर, द फर्स्ट एंड थर्ड ओवर देयर. सेकेंड टॉपिक में हमारा रूम प्रॉब्लम था. सो लेट मी जस्ट कवर this topic first. No, this one. Magma rise and emplacement. So definition of intrusive igneous rock. These are magma that did not reach the surface and they are solidified beneath the earth's crust. Unlike volcanic eruptions, plutonic body magma intrusions, they lack dramatic surface activity, but they contain significant volumes of the igneous rock. Magma formation. Magma forms when solid rock is melted due to processes, temperature increase, decompression, and the introduction of fluids. The magma segregates from the unmelted solid to form a liquid mass. Now we have buoyancy and magma rise. Magma is less dense than the surrounding solid rock, which makes it buoyant. Diapirism. This is a process where buoyant magma rises through the surrounding material, ductile rock, in a manner similar to how a salt diapir form. Salt diapir, halite salt, behave ductile under low pressure and rises when covered by a denser rocks. In the case of magma, it rises in diapiric fashion if the surrounding rocks are sufficiently ductile. Now we have pushing upwards through the overlying rock layers. Now rising magma in brittle layers. So when magma encounters less ductile, more brittle rock layers, it cannot rise as easily as in diapiric manner. It often exploits the pre-existing fracture, faults or weaknesses in the surrounding rock. So it has given us a bit insight कि magma rise and emplacement में basically क्या है. इंट्रूसिव इग्नियस रॉक मैंने बता दिया कौन से होते हैं. मैग्मा फॉर्मेशन कैसी होती है, इंक्रीजिंग टेम्परेचर, डिकम्प्रेशन और फ्लूइड्स के वजह से, जिसकी वजह से मैग्मा सेग्रीगेट हो जाता है अनमेल्टेड सॉलिड से, जिसके अंदर वो लिक्विड मास बनाता है. बायंसी एंड मैग्मा राइज. डायपिरिज्म क्या होता है कि बायन मैग्मा जो है राइज करता है सराउंडिंग मटेरियल डक्टाइल होकर इन सिमिलर मैनर जैसे कि सॉल्ट डायपिर फॉर्म होते हैं. डायपिरिज्म हेलाइट जो है वो भी अंडर लो प्रेशर बिहेव्स डक्टाइल अंडर लो प्रेशर एंड द राइजेज व्हेन कवर्ड बाय द डेंसर रॉक. नाउ ब्रिटल लेयर्स में थोड़ा सा मुश्किल हो जाता है सो इट दे कैन नॉट राइज इजीली एज इन डायपेरिक मैनर. सो फिर वो क्या करता है, वो प्री एग्जिस्टिंग फ्रैक्चर्स, फॉल्ट्स, वीकनेस इन सराउंडिंग उसको एक्सप्लॉइट करता है. नाउ वी हैव हाइड्रोथर्मल सिस्टम. सो डेफिनेशन ऑफ हाइड्रोथर्मल सिस्टम. दीज सिस्टम्स आर फॉर्म बाय द सर्कुलेशन ऑफ वाटर often heated by magma through permeable rocks, which leads to the development of fumaroles, not springs and other hot springs as well as the other surface features. Now we have formation of hydrothermal fluids, so magma heat. Shallow magma chambers heat groundwater, causing it to rise through permeable rock. Some of the fluid may be juvenile from the magma itself, while rest might be meteoric from the rain or snow melt. Convection, the heated water rises and spreads laterally, cools that descends due to the increased density, creating a convective system. Now we have hydrothermal fluids and mineral alteration. So fluid rock interaction. Hydrothermal fluids interact with the surrounding rock and leading to the alteration of minerals and the precipitation of new minerals. Alteration products, so these include quartz, feldspar, chloride, calcite, epidote, and sulfide ores. Alteration and ore deposition often follow the temperature and chemical gradients, resulting in zone alteration pattern. Now we have economic mineral deposits. Hydrothermal systems are a significant source of economic ore deposits, including the metals like gold, silver, copper, and zinc. Now, hydrothermal systems at oceanic ridges. Oceanic hydrothermal system at oceanic ridges, seawater and juvenile fluid interact with the oceanic crust, forming the hydrothermal system that deposits metal sulfides and support the unique biological communities. So, hydrothermal system is a very interesting topic in this chapter. ये कैसे होता है कि जब आपका वाटर का सर्कुलेशन होता है जो कि मैग्मा से हीट हो गया, permeable rocks थ्रू परमिएबल रॉक्स, एंड इसकी वजह से फ्यूमारोल्स, हॉट स्प्रिंग्स, सल्फारोल्स, ठीक है, इनकी वजह से वो बनते हैं. नाउ वी हैव मैग्मा हीट. तो शैलो मैग्मा चैम्बर्स जो वो ग्राउंड वाटर को हीट करते हैं जिसकी वजह से वो राइज करते हैं परमिएबल रॉक में. हाँ जी, तो वाटर जो इसमें होता है वो जुवेनाइल होता है, जो कि हमारा फ्रॉम द मैग्मा इटसेल्फ, एंड द मीटियोरिक दैट इज rain or snow melt water. Convection, the heat water rises and spread lately and they cools then descend down due to increased density. Now we have fluid rock interaction. So hydrothermal fluids interact with surrounding rocks, and sometimes we have so fluid rock interactions we have in hydrothermal fluid. We have alteration products as well as we have economic mineral deposits and oceanic hydrothermal systems as well. So key terms that we need to take from it: diapirism, a process where buoyant magma rises through ductile surrounding rock, and where there is no ductile surrounding rock, there is a brittle surrounding rock. So magma then exploits the place formations like faults as well as spacings. Now plutons, it's a body of intrusive igneous rock formed from cool magma. Now we have stopping, the process by which rock blocks are dislodged from the roof of an intrusion and they sink into magma. Assimilation, the process where magma melts and incorporates surrounding country rocks. Hydrothermal system, a convective system where heated water circulates through rocks even due to the presence of shallow magma. Now we have okay, so now we have this room problem. ये तो आपका okay. Room problem. So room problem in geology, it refers to the fundamental question how large intrusive igneous bodies, pluton, batholith, laccolith, create space for themselves as they move through and solidify within the Earth's crust. Since magma is injected into solid rock, geologists have debated how enough space can be made to accommodate this large volume of molten material without completely disrupting the surrounding rock. So key challenges of the root problem कि problem इसको कहा क्यों गया है. Magma cannot just push rock aside. Solid rock is rigid and the immense pressure at depth making it difficult for magma to intrude without displacing the existing materials. That is correct. Now we have no large open voids exist at depth. Unlike near surface environments where magma can flow into open fractures, deeper regions of the crust do not contain empty spaces for magma to fill. Volume displacement issue. Large plutons can be tens to thousands of kilometers across, meaning a significant amount of surrounding rock must be displaced, altered, or altered to accommodate them. Now we have the proposed solution to the room problem. So geologists have proposed several mechanisms by which intrusive bodies can move through crust and make room for themselves. Lifting the roof, doming, and faulting. So plutons like laccoliths can push the overlying rock upward, creating domes. Faulting, so what they have proposed as a solution. So lifting the roof, doming and faulting. So जैसे कि लैकोलिथ होते हैं वो overlying rock को up can push the overlying rock upwards and then they create the domes. Faulting can lift block of crust, forming spaces for magma to intrude. Now we have melting of country rock, assimilation. So magma partially melt the surrounding rock and incorporate it, reducing the need for physical displacement. However, this is limited by amount of heat available in the magma. Breaking and sinking as well as stopping. So overlying rocks may break into fragments and sink into the magma. Evidence includes xenoliths, but large-scale stopping is questioned due to a lack of significant stop rock remains. Now we have ductile deformation and downward flow. At greater depth, the country rocks may deform and sink around the rising magma, helping create space. This process is most effective when the both magma and surrounding rock have similar viscosities. Now we have the magma injection over time, incremental growth. Instead of single large intrusion, batholiths may form by multiple small magma injections over millions of years. Dikes and sills complex allows magma to gradually accumulate, reducing the need for immediate large-scale displacement. Extensional tectonics and fractures. So the increase in regional extension fracture open, allowing magma to intrude more easily. This explains why some large plutons are associated with tectonic rift zone or shear zone, as we have in the Deccan plateau, like Deccan volcanism. Now, modern understanding. So, recent studies have suggested that the large batholiths likely form incrementally over time rather than intruding all at once. Magma move up via dikes and sill, spreading in tabular or wedge-shaped bodies rather than ballooning outwards. This reduces the need for vast amount of space and helps explain how these massive igneous bodies fit within the crust. So this is the room problem जिसके ऊपर हमारे जीएसआई में क्वेश्चन आया है, एंड आई एम प्रिटी श्योर कि अगली बार इससे और थोड़ा सा अच्छा क्वेश्चन आ जाएगा जिसके अंदर आपके 4 रीजंस दे दिए जाएंगे कि इसके अंदर प्रॉब्लम है किस लिए, एंड यू हैव टू चूज कि इज इट राइट और नॉट. सो दिस इज द फ्यूचर. नाउ इफ आई मे टेल यू कि रूम प्रॉब्लम किससे एसोसिएटेड होती है. ये प्लूटोनिक्स इंट्रूसिव इग्नियस रॉक से एसोसिएटेड होती है, पर्टिकुलरली ग्रेनाइट से और अदर फेल्सिक टू इंटरमीडिएट कॉम्पोजिशन से, जो कि बैथोलिथ, प्लूटोन, लेकोलिथ सिल में हमें मिलते हैं. दीज आर द लार्ज बॉडीज ऑफ मैग्मा दैट कूल्स एंड क्रिएट crystallized beneath the Earth's crust. Now we have granite. They are common in batholith and large plutonic bodies, diorite, found in intermediate plutonic complexes, gabbro. They occur in mafic intrusion, but less commonly in batholith scale structures. Tonalite and granodiorite, they are typically in continental magmatic arcs. So this igneous intrusive form at depth. The room problem arises because magma must displace the pre-existing country rock without creating large voids. This problem is particularly significant in felsic magma because they are more viscous and tend to form large, slow moving protons rather than small and easily emplaced dikes. So if I may come to the one last revision that what we have done till now. So today, not the whole case scenario. So magma rise and emplacement, the room problem, magma formation and buoyancy. I have told you magma जो है डेप्थ पे फॉर्म होते हैं ड्यू टू पार्शियल मेल्टिंग, और फिर वो इट गेट सेपरेटेड फ्रॉम द रेसिडुअल सॉलिड्स, और फिर बीइंग लेस देन द सराउंडिंग्स वो बाइंड होते हैं और राइज कर जाते हैं. इसी केस में आपके डायपिल्स फॉर्म होते हैं. डायपिल्स में सॉल्ट डायपिल्स आपका अच्छा एग्जांपल है. इनकी लो डेंसिटी होती है और ये बिहेव करते हैं डक्टाइल मैनर में एंड राइजेस व्हेन द ओवरबर्डन कंपैक्ट्स. So magma diapirs were traditionally thought to rise similarly through the mantle. In less ductile upper mantle and crust, magma exploits the fracture, like as I told you in the brittle case scenario. Room problem in magma emplacement. So magma requires space that it move upward. So they displace, assimilate the country rocks. Open voids exist only near the surface at depths. Fractures are forced close by the lithostatic pressure. So magma must displace or incorporate the surrounding rocks to rise. Now we have mechanism how for the pluton emplacement. How does it? Roof lifting, plutons. Lacolith lifts the overlying rock by folding, by block uplift along the faults limited to shallow depth 2 to 3 km due to required magmatic overpressure. We have assimilation melting through country rock. Magma melts surrounding rock creating space limited by latent heat of crystallization, which reduces magma mobility. Now we have stopping, breaking and sinking. So brittle rock, it just brittle roof block breaks off and sink through the magma. Xenolith in some plutons, but it's not always effective due to need for the blocks to be denser than magma and slow sinking in viscous magma. Now we have ductile deformation and downward flow. So heat from the plutons soften the rock, allowing the downward flow. Some batholiths show structural evidence of isostatic sinking into deeper crust. We have ballooning, that is radial expansion, and magma chambers. So magma inflow causes expansion, forcing the walls apart, requires similar viscosity between magma and country rock. Extension and dike injection. So magma exploits the extension fraction and injects as dikes and sills. Rate of extension limits effectiveness. Modern view told you. Batholiths may be shallower than previously thought, and based on gravity models, experiment work suggests diapirs thin out near the surface. We have tabular or wedge-shaped plutons reduce the space requirement. Incremental growth over the million of years, that is the most accepted one, like dike feed magma intrusion, they followed by the lateral sill spreading. And then we have the roof elevation or floor depression contributes to volume accommodation. Evidence of sheeted and nested plutons suggesting stepwise growth. So we have the conclusion. The room problem remained debated, especially for the giant batholith till now. These suggested the thin tabular plutons within the multiple water injection over time, and the combination of incremental growth, dixel complexes, and crustal deformation may be the best explanation for large batholith emplacement. So with this, I will end the chapter 4, and now we'll focus on the chapter 3, I guess, and with this, I'll end the video. Thank you.